Hello everybody, this is Naveen Sapare, Assistant Professor, Department of Mathematics, KLIT Hubli. So today we will continue Fourier cosine and sine transform. So in the last uh, class we discussed about the mathematical form of cosine and sine transform and we solved a few problems. So we will continue the same today and we'll solve some more problems. Find the infinite Fourier cosine transform of e raised to minus x square. So obviously to find the Fourier cosine transform we have a mathematical form. Fc of u is equal to integral between 0 to infinity f of x into cos ux with respect to x. So this is the mathematical form of Fourier cosine transform. Here we need to substitute just a given function, that is e raised to minus x square. So given that f of x is equal to e raised to minus x square. So substituting f of x is equal to e raised to minus x square into cos ux with respect to x, and obviously this is fc of u. Now we need to evaluate this integral, and since we know that this integral is not in the standard form, so that we can evaluate it directly by using a mathematical formula, that is integral formula. Therefore what we need to do is, first we need to reduce this integral into the standard form so that we can easily evaluate the integral. So that here we use a Leibniz rule. What is the Leibniz rule here? Leibniz rule is a method we use it to reduce the integral into the standard form. In the Leibniz rule, we are going to differentiate this integral under the integral sign with respect to not x, with respect to other than x. So here we are having one more parameter, that is u. So we are going to differentiate under the integral sign with respect to u, and that is called as the Leibniz rule. And I just said that Leibniz rule will be used whenever we need to reduce the integral into the standard form. Therefore, differentiating under the integral sign with respect to u partially. Obviously, when we use a partial derivative, then definitely we are differentiating with respect to u here. So when you are differentiating with respect to u, definitely we consider remaining variables as a constant. So differentiating, we have dfc by du is equal to integral sign will remain as it is 0 to infinity, e raised to minus x square will be constant, and the derivative of cos ux with respect to u will be minus of sin ux into x with respect to x here. So now definitely still the integral is not in the standard form, so we make use of some adjustments. So for that I'm going to multiply numerator and denominator by 2. So I have here 1 by 2, so 0 to infinity, it is, I will take this sin ux first, into bracket I am going to write this e raised to minus x square into 2x. This is a small adjustment. Okay, so why this adjustment? Just to apply the integral by parts. So we will take this as u and this as v. We have an integral by parts, that is integration of u into v. The formula will be, here we have a formula, integral of u into v is nothing but u into integral of v1 minus integral of v1 into derivative of u. It means that here we are taking sine ux as u and this e raised to minus x square into 2x as v. So we don't have the formula for integration of e raised to minus x square into x. That's why we multiplied the numerator and denominator by 2. Again, if you cancel this 2 and 2, again you will get the previous step, and obviously there is a minus sign outside. So by multiplying numerator and denominator by 2, we can reduce the integral into the standard form of integral. So, and the integration, obviously I am taking this as v here and I am going to take this as u when you compare with a standard formula. It means that we need to have the integration of e raised to minus x square into 2x. Now applying this integral by parts, so we have dfc by du is equal to, I will keep this sine ux as it is, into integration of e raised to minus x square into 2x will be, it is minus of e raised to minus x square. Obviously I will put a bracket here and there is minus. Okay, so here applying the integral by parts, taking this as u and v, so I kept this minus outside, that is minus 1 by 2. Here it is minus 1 by 2 sine ux, and integration of e raised to minus x square into 2x will be minus of e raised to minus x square minus integration, just refer this formula u as it is, integration of v. Okay, it is integration of v, not v1. So integration of v means integration of e raised to minus x square into 2x will be minus of e raised to minus x square minus again integral into v1. v1, what it is, v1, v1 is nothing but again it is minus of e raised to minus x square. So minus into minus become here plus e raised to minus x square into du. Du is nothing but it is derivative of sine u. So derivative of sine ux is nothing but cos ux into u with respect to x. And since the limits are between 0 to infinity, and here also the limits are between 0 to infinity. So next, dfc by du, that is derivative, is equal to, applying the limits for this first term, so upper limit is infinity, therefore e raised to minus infinity will be 0. So 0 into anything become 0, and coming to the lower limit is 0, so sine 0 will be 0. So this whole term become 0 here. So remaining is, so only minus 1 by 2 integration, the second term, that is 0 to infinity e raised to minus x square into cos ux with respect, obviously there is u here, into u du. Next step, again we need to evaluate this, so it is dfc by du is equal to minus 1 by 2 times of. Now definitely just observe this integral. So obviously here there is u, so I will take that u outside and observe this integral 0 to infinity e raised to minus x square into cos ux, which is nothing but fc of u. So I will write, instead of fc of u, I just write fc. Obviously here dfc is nothing but it is derivative of fc of u. So in short I have written only fc. Now obviously I got this step. Now we need to separate the variable and we need to integrate it. What is our intention? Our intention is to get the value of f of c, but here we are having a derivative of f of c, so we need to get f of c here. Therefore we try to separate the variables. So dfc by fc, and I will take this to this side. In the numerator is equal to, here we are having u, that is minus u du. Okay, so just cross multiplying this du. Now evaluating the integral, we have here 2 times of log of fc is equal to minus u square by 2. So intention is to get fc, therefore we need to separate the variables and integrating, plus some constant log of k here. Therefore this is nothing but log fc, that is log fc the whole square is equal to minus u square by 2 plus log of k. In the next step we take this log this side and we get log of fc square minus log k is equal to minus u square by 2. So log m minus log n will be log of fc square divided by k is equal to minus u square by 2. Now taking a anti-log here, so when you take anti-log it becomes fc square divided by k is equal to, it becomes exponential function e raised to minus u square by 2. That is nothing but, here we have fc square is equal to k times of e raised to minus u square by 2. So obviously finally we have the answer fc is equal to, it is square root of k into e raised to minus u square by 2, and hence that's the solution here. Let us take the next problem, that is find the Fourier sine transform of e raised to minus ax divided by x, where a value is greater than 0. So here also the function f of x is given, so we need to compute sine transform. So we have fs of u, that is Fourier sine transform, is equal to integral 0 to infinity f of x into sine ux with respect to x. And since given that f of x is equal to e raised to minus ax divided by x, now we need to replace this f of x as e raised to minus ax by x. So it is integration 0 to infinity e raised to minus ax divided by x sine ux with respect to x, and this is nothing but fs of u here. And since this integral is, again it is not in the standard form, so that we need to reduce this integral into the standard form by using the Leibniz rule. I just said that Leibniz rule is a method or the procedure by using that we can reduce the integral into the standard form. And in the Leibniz rule we just try to differentiate it under the integral sign with respect to other than this x. So we are going to differentiate partially with respect to u. So we have here dfc by du is equal to 0 to infinity e raised to minus ax divided by x, and the derivative of sin ux with respect to u will be cos ux into x with respect to x. So differentiating under the integral sign means we get one extra x here, so that we can cancel both the x's, so that easily the integral reduces into the standard form. So we have dfc by du is equal to, both x cancels here, so remaining is 0 to infinity e raised to minus ax into cos ux with respect to x. Then definitely this integral is easily integrable, and for that we have a formula. So integration of e raised to ax into cos bx with respect to x is given by e raised to ax divided by a square plus b square into bracket a into cos bx plus b into sin bx. So this is the integral formula, and the same formula we will use here. So it becomes, now applying e raised to minus ax into cos ux, here a is nothing but, when you compare with this standard form, we come to know that a value is minus a and b is nothing but u. Therefore it become dfc by du is equal to e raised to minus ax divided by a square plus u square into bracket minus a into cos of ux plus u into sin of ux, and applying the limits 0 to infinity here. So once again applying upper limit as well as the lower limits after the integration. So upper limit is infinity, so e raised to minus infinity become 0. So 0 into anything will be 0, and now taking the lower limit, and while taking the lower limit we need to take a minus sign every time, and e raised to 0 will be 1 divided by a square plus u square. Inside the bracket cos 0 will be 1 and remaining is here minus a, and since we know that sin 0 will be always 0, and finally we have dfc by du is equal to, minus into minus become plus, so it becomes a divided by a square plus u square. So we have the derivative of fc, but we need fs, sorry, we need a fs of u. So there is a small correction here, that is, it is fs. So fs of u we need. So to have fs of u, we need to integrate it in this stage, okay, because we are having a derivative but we need a fs of u. So integrating with respect to u, we have fc of u is equal to integration of a divided by a square plus u square is nothing but tan inverse of u by a plus some constant c, and hence this is the general solution. But to get a particular solution, I just put a value of u here, put u equal to 0, then this fc of u become fc of 0 is equal to tan inverse of 0 is nothing but 0 plus c, and since the value of fc of 0 is nothing but, so once again it is a fs not fc, it is fs, this is also fs. So fs of 0, so just substituting u equal to 0 in this fs of u. So when you put u equal to 0, this sin 0 becomes 0, and 0 into anything will be 0. Therefore, we can consider fs of 0 value as 0. So therefore, we have c value as 0 here. So once we get the value of c, substitute the c value in this fs of u. And finally, we have fs of u is equal to tan inverse of u by a, because the value of c is 0, and hence this is the Fourier sine transform of the function e raised to minus ax divided by x.